Hey everyone, so today we'll be going over experiment 13, which is the wave nature of the electromagnetic spectrum. So in this laboratory, we will be using two different experimental apparatuses. The first will be using a helium neon laser, and the second a microwave source in that setup over there. The purpose of this lab is to investigate the wave-like nature of electromagnetic radiation, or light. And so we do this by observing the interference pattern generated by these two apparatuses. So, as some background, classically, physicists have looked at light as a particle, or a photon, which classically should travel in straight lines. However, following the 19th century, quantum physicists have developed a different perspective of light, namely its wave nature. And so today, that is exactly what we will be looking at. So some helpful hints that will be guiding you through your post-lab are, one, knowing how to accurately draw and scribe down the interference pattern shown on this board over here, as well as knowing the error values associated with the measurements you take. So first we're going to demonstrate what a typical diffraction pattern will look like. So, as you can see in this board, there are interference patterns of the light as a result of the diffraction grating, and there are different maximum and minima of each fringe, and different patterns in each. This is what we'll be drawing in the multiple graphs on your post-lab. And secondly, the other helpful hint for your laboratory is making sure the values for your error measurements are accurate and reflect the precision of each measurement. So over here we have the vernier scale. This is what you'll be using to determine the width of your slits. And this has a precision of 0.05 millimeters. It is standard convention that for any analog measurement system that you use, the error associated with that measurement is half of the smallest measurement increment. So in this case, the error associated with this scale, with a precision of 0.05 millimeters, is half of that, which would be 0.025 millimeters. Again, this system is measuring the slit width, which is D in the laboratory note. You'll be also measuring the distance from the slide to the board, and this distance is L. Because we will be measuring this distance using rulers, the smallest increment will be 1 millimeter, and so the precision associated with this device is 0.5 millimeters. Similarly, each square tick box on this board is 1 millimeter, so the precision associated with this measurement is 0.5 millimeters. So now we're moving on to the second apparatus and how that apparatus will work. So this is an example of what your graph should look like. And the center fringe is the most intense, and that should be reflected in your image here. The outlying fringes should be less intense and should be noted here as well. So again, it would be important to accurately represent both the position and intensity of the different fringes in your pattern. Okay. Hold on. Let me just go back. This concludes section 3.2 of the laboratory experiment. In section 3.3, we'll be observing the different interference patterns generated by the 4-slit and 6-slit diffraction grating. This pattern over here was generated by the 4-slit interference pattern. You'll need to copy and sketch as accurately as possible both the position and intensity of these fringes onto your graph. in the post lab. This interference pattern here is generated by the 6-slit diffraction grating. As you can see, it is slightly different from the 4 and 2-slit diffraction grating. As you can see, it is slightly different from the 4-slit and 2-slit diffraction grating patterns. However, there are still the characteristic 3 fringes, 1, 2, and 3. Similarly, you will need to copy and scribe these fringes onto your graph in your post lab. This concludes section 3.3. In section 3.4, we will be using a slide screen as our diffraction grating, shown here. This is the interference pattern generated by a wire screen. It is unique and vastly different from the previous diffraction gratings we have used. Note the horizontal and vertical structure of the interference pattern and the characteristic tick boxes for each. In this section, you will have to scribe and copy down as accurately as possible both the position and intensity of the pattern in your graph in your post lab. This concludes section 3.4. So this is the second part of this laboratory, and in this experiment we will be using a microwave source instead of a helium neon laser to investigate the same phenomenon as in part 1, namely investigating the wave-like nature of electromagnetic radiation, or light. And so in the setup we'll be using a double-slit diffraction grating and measuring the incoming radiation from the transceiver. So in the setup we have a microwave transmitter and a microwave receiver, and the incident radiation is a function of angle. As you can see that this arm pivots, and there's an angle wheel provided. So we can set up the experiment by putting up the double slits with a given distance d that we will be measuring with a caliper. And in this setup, we need to know specifically how this setup differs from part 1. Namely, the equation that we'll be using does not make the small angle approximation. And so the resulting equation we'll be using is d sine theta is equal to n lambda, where n is an arbitrary integer. So like in part 1, there will be errors that arise because of your measurement taking. In this case, it will be from the angle wheel. Because the angle wheel has 360 degrees, and the smallest increment you can take is 1 degree. So the error associated with this device would be 2 pi over 360 divided by 2, or pi over 360. So now we move on to the second part of the experiment. First, what we will want to do is install the double slit screens. Do that by putting it here and here. Although not mentioned in your laboratory handout, we will want to have the slit widths to be 1.5 centimeters. Although not mentioned in your handout, we want the slit widths d to be 1.5 centimeters. And so we can do that by measuring using the caliper. First, I'll use a ruler to estimate a ballpark range of 1.5 centimeters. and then we can use the caliper for a more precise measurement. Now that the slide has been installed, we want to ensure that the double slit is perpendicular to the two horns. Now we can begin our experiment. We begin by setting the amplifier to be at the lowest setting, which is an amplification of 1. We begin by taking the data point at the 180 degree mark or 0 degree mark. Once we have taken the data point at the 0 degree mark, we take measurements in this direction as well as in this direction. We'll be taking a measurement of intensity in milliamps every 5 degrees in one direction and repeat in the other direction. Once we have finished taking the data for each direction, we will note the minimum and maximums for each direction. For example, once you have taken the measurements for increments of 5 from 0 to 35 degrees, we will repeat for the second direction.
the data we collect today will be given to you in order for you to complete your postdoc.